Okay, so I've started recording. Hello everyone. In this session, we'll be going over these libraries. So last week you learned probabilities and probability distributions. So we'll see how we work with them in Python. So the first part of today's session will be more of a tutorial. So we'll learn to use NumPy and SciPy. Afterwards, we'll see how do you use the discrete and continuous distributions using SciPy. How do you work with the mass functions, the density functions, and how do you plot these functions, how do you sample from these functions, things like that. And finally, we'll see how do you answer maybe numericals. For example, you get let's say probability of at least this much success in a, let's say, bell curve. What are the odds of being in this region and that? How can you do that using Python rather than doing it on paper? Okay, so uh, as usual, we'll be going over it in Colab. So, by the way, last time someone had an issue with Colab. So, is that resolved? Is that person here? Okay. Yeah, and one last thing, if anyone has a doubt or a question, so rather than writing it in the chat, please speak up. Okay, so because I don't get any notifications when you write it in the chat. Okay, so let's start. We are working with NumPy. NumPy stands for numerical Python. So as pandas is used for working with data frames, NumPy is used for working with matrices. So you do import NumPy as NP. Yeah, just a minute, it's connecting.
So we can't see your screen.
Oh, just a minute, sorry. So can you see it now?
Yes, sir.
Yeah, thank you. Yeah. So I was saying we'll import the NumPy library, and normally in Python, for example, you will use lists, that is, let's say 1, 2, 3, and 4, and so on. But you cannot do mathematical operations on that. Let's say L into 5 will just duplicate the list 5 times rather than multiplying the values of the list by 5. So to ease this, what you do is you create a NumPy array. So the first thing is, how do you create an array? Okay, so create a NumPy array. To do that, you say np.array and you supply it any iterable, a tuple, a list, or something. So in our case, let's say 1, 2, 3, 4, and 5. It creates a NumPy array. So let's say we'll save it in ARR. So now we have an array. Okay, a NumPy array. So you can do basic functions with that. Let's say array multiplied by 5 multiplies every element by 5. You can say maybe plus 5. So it does that. So we cover creation of NumPy arrays like that. So every NumPy array has some features assigned to it. For example, we will have shape, we will have size, and we have type, maybe d type. So we see that array.shape basically tells you that it is a one-dimensional array having 5 elements. The second says you have a total of 5 elements. You will say, I mean, there is no difference between the first and the second one, but when you go to multi-dimensions, you'll see the difference. Finally, you will have d type. D type says that all of your elements are integers. Okay, so let's say instead of working with a single dimension, you want to work with a matrix. So in that case, you will supply a list of list. Okay, so let's say I have a list where the first row is 1, 2, 3, and the second row is, let's say, 4, 5, and 6. If we print the array,
could you zoom
so
just a little bit, sir?
Okay, is this okay?
Yeah, it's okay.
Okay. Yeah, so you have a two-dimensional array where you have the first row as 1, 2, 3, and the second row as 4, 5, 6. If we check the parameters once again, we'll see that our shape is 2 by 3 because we have 2 rows and 3 columns. We have 6 elements in total, and everything is still an integer. Make sense? Any questions? Okay, moving on. So you can add, subtract, multiply, divide, any normal thing that you can do with a matrix, you can do with two NumPy arrays. So let's say we have one as np.array 1, 2, 3, 4, 5, 6. So let's say you have these two. So to add them, you can simply write ARR plus ARR2 and it will add the two. In case you want to multiply the two matrices, there are two types of operations. You can either do it element wise or you can do normal matrix multiplication. Okay. So let's say we have ARR times ARR2. This is an element wise multiplication. So you see 1 into 1 is 1, 2 into 1 is 2, 3 into 1 is 3, and so on. But if we want to do a matrix multiplication, we use at the rate. So in this case, it will check that the shapes do not match. They are not correct shapes for multiplication because we have a 2 by 3 multiplied by a 2 by 3. So these don't conform to the shapes required for matrix multiplication. In matrix multiplication, these two should have been the same. Okay, so let's say we work with its transpose. This time it will work. Any questions?
Sir, can you please repeat it?
Sir, if matrix multiplication wasn't working, then how did it make transpose of it?
Yeah, so what we did was we took a transpose of ARR2. Okay, so now it became a 3 by 2 matrix. You see, it became a 3 by 2 matrix. And we are multiplying it with a 2 by 3 matrix. So now we can multiply the two. Make sense?
Yeah, sir. Okay.
Okay. So just to keep track, we saw creation, we saw basic operations, we saw shape, size, and type. Okay. So now let's say you want to create an empty NumPy array. So how do you do that? Let's say you want to create an array of size, let's say 10 by 200. You cannot basically write down this many numbers. So to do that, you can simply say, okay, np.array, and let's say size is 10 by 200. And if we try again, we see that the shape is 10 by 200. There are 2000 elements, and by default, the type is float. You can supply the type, that is, I want an integer, I want a float or something like that. So similarly, you can also make a vector full of zeros. So let's say we will say np.zeros, and again 10 by 200. Same thing. And we can do ones as well. So np.ones 10 by 200. So ARR will be random numbers. So these are random numbers. 0 will have all zeros, and ones will have all ones. Okay. Any confusion? So one last thing is, let's say you want to create an array of, let's say like this, 1, 2, 3, 4, 5, 6, a sequence. So there is a shortcut for that, that is np.arrange, and you tell it to start, let's say at 4 and end at 16. So if we do that, we get a sequence of numbers 4, 5, 6 starting at 4 and ending 1 before the element supplied. OK, so it starts at 4, ends at 15. We can also supply a jump parameter. So let's say I wanted to add 3 at every step. So we have 4 plus 3 is 7 plus 3 is 10 plus 3 is 13 plus 3 would have been 16, but we don't want to go to 16. OK, so this is the step function. Now let's say I have this function, that is I say OK, np.arrange 0 to 16. I get a total of 16 elements, but I want to convert it to a 4 by 4 matrix. Right, I have 16 elements. I can create a 4 by 4 matrix out of that. So to do that, you say, let's say A is an array, and if you print A, you get a sequence like this. If you
So
do A
what
dot,
data you have loaded, because it's giving me errors, sir.
at what part are you getting an error?
I'm, here it is, the chat box.
np.arrange 4. Did you import NumPy?
Yeah, I imported.
So what does your error say?
This is the error.
I mean, did you import it as NP or did you just do import NumPy?
I imported NumPy as NP.
I mean, it should work.
But before something data you have loaded.
No, I haven't loaded anything.
You didn't loaded any data?
No, no, no. For example, if I run your command, it works on my side.
Okay, but
Just
giving me
restart.
error, sir.
Yeah, just restart your notebook. Make sure you import NumPy as NP, and it should work after that. I mean, it works on my side.
Okay.
Yeah. So I was saying, let's say we have a matrix of size 16 and we want to convert it to a 4 by 4 matrix. So the way you do it is disconnected. Just a minute. So you write a dot reshape and then you tell it to reshape it as a 4 by 4. So now we have a 4 by 4 matrix. Any confusion in this part? Now let's say you store this 4 by 4 in a new matrix and you want to get back to a flat matrix. So what you do is you say b dot ravel and you again get a flat matrix. OK. So we covered this and we have ones, zeros, arrange, empty, and reshape. I think this much should be OK. Shape, manipulation, stacking. Yeah. So for example, we have a matrix like this. You were able to index your pandas data frame. Remember, you used to do something like df.iloc, and then you would say, I want the, let's say, the second row and the third column, right? So it works the same way in NumPy, except that you don't write iloc. For example, if I have to work with B and I want the, from the first row, I want the second element, I'll just say B, the first row, the second element, and it will return 6. The way you used to index, for example, I'll say give me everything up to the second row and give me all the columns. So it gives me the 0th row, the first row, and all the columns. I can also say, OK, give me only columns after 2. So it returns 2637. So indexing is the same as you do it in pandas. The only thing is you don't use an iloc. Make sense? OK, so maybe for the people who are new here, These sessions are being recorded and will be uploaded to YouTube, and this notebook will also be shared on GitHub. So no need to worry about that. So we have shape manipulation. Yeah, we have covered this much. So, So why are we learning NumPy if we have to work with distributions? The thing is, we want to use a library known as SciPy, which stands for Scientific Python. Every array in SciPy is a NumPy array. So to use SciPy, yeah. Does anyone have a question?
So could you explain the previous point B of colon 2 and
Yeah, this one. Yeah, so I was saying the way you index a NumPy array is the same with you index your pandas data frame. So let's say you have a pandas data frame DF, and I want you to index the first row and let's say column 3. So you would write df.iloc, the first row, third column, right? In NumPy, let's say you have an array ARR and you want the same thing. So what you do is ARR 1 and 3. You just don't write ILOC. The indexing works the same way. And as far as colons are concerned, it's the same as in data frame. Let's say in your data frame, I would tell you, give me the first 10 columns, 10 rows, and let's say third to fifth column. So you would do like this, give me the first 10 columns and give me everything from 3 to 5, right? So here you would do it the exact same way, just remove ILOC. So give me the first 10 and give me from third to fifth. Clear?
thank you.
Okay.
What is the use of ravel function, sir?
Yeah, so
is written.
yeah. So you have a matrix, let's say a multi-dimensional matrix. This is a 2D matrix. So if you want to flatten it out, that is first row, second row, third row, fourth row, you write b.travel and it flattens the entire matrix into a single line. Clear?
Okay, sir. Thank you.
Yeah, so I was saying we
So
have
what
to
are
work with
functionalities possible under NumPy, sir? What other calculations we can perform?
Yeah, so NumPy, before deep learning came around, NumPy was the default library for working with matrices or working with tensors. So let's say you have to do any sort of matrix multiplication, you have to use NumPy because you can easily create matrices and you can easily do operations on them. Nowadays, people use, let's say, Torch, PyTorch. It works with tensors and it has GPU support. NumPy does not have GPU support, so people have moved on to PyTorch. But if you have to work on the CPU, NumPy is the go-to.
Mm-hmm. What do you mean by tensors actually?
Yeah, so let's say you have a number 1. This is a scalar. Okay. If you have, let's say, a sequence of numbers like this, and they are only in one direction, so this is a vector. If you have 2 dimensions, let's say something like this, this is called a matrix. 2 dimensions basically. Any matrix that has 3 or more dimensions is called a tensor. It's just basically lingo. So you have more than 3 dimensions, 3 or more dimensions, it's called a tensor. NumPy can also work with more dimensions. It's just that it doesn't have GPU support. That's it. So let's say I create a 3-dimensional tensor. Let's say np dot zeros. I'll say give me 2 by 3 by 3. Cannot interpret 3. Yeah. So what's happening here is first it will create a 3 by 3 matrix. Okay. And then it will create 2 of them. So let's say I said 10 3 by 3. That would mean create a 3 by 3 matrix and I want 10 of those. I mean, in this case, it is 0, so everything looks the same, but they need not be the same. Yeah, Sangam, do you have a question?
Please repeat again np dot line number 40.
Line number?
NP dot is 0. So I can't
Does it?
understand NP. Yes.
Yeah, so did you join late?
Yes.
Yeah, so np.zeros basically creates a matrix of size whatever you provide. So I ask it to create a matrix of size 2 by 3. All of them should be zeros. So if I ask it to do, let's say 2 by 2 by 3, it means create two matrices, each of which is 2 by 3. Make sense?
Thank you, sir. Got
So
it.
you can add any number of dimensions here. So let's say I ask it to create 10 of these. Each of them should have 2 of these, and every one of them is a 2 by 3 matrix. So it's a hierarchy. Okay, 10 of
Got
these things, 2 of these things, and so on.
Yes, got it.
Okay. So I was saying we will be working with SciPy because you have studied probability and distributions in your lectures. So NumPy, so SciPy is basically NumPy plus some basically probability, statistics, all of those functions. So it builds on top of NumPy. So the first thing that we'll go over is yeah. So let's say we create an array. We create an array 1, 2, 4, 100, -1, and so on. And we want to find the, let's say, mean, mode, kurtosis, skewness, things like that from this array. So rather than computing them by hand, what you can do is, let's say we have from SciPy import stats. So SciPy has several sub libraries. We'll be working with stats for statistics. Okay. So what we do is stats.describe ARR. So it returns the min max, that is the minimum is -1, the maximum is 199. Your mean is this, your variance is this, your skewness is this, your kurtosis is this. So any distribution that you may have, if you call describe on that, it will give you these basic features of that distribution, as you read in the first week. So to access individual functions, so let's say we store this in something, let's say DESC, we can say DESC.mean. So it will return the mean. Similarly, we can say it's a skewness. So you will have skewness. So to view everything that you possess, I believe maybe keys will work. Yeah, no. Yeah, so you can basically supply these numbers, let's say mean, variance, kurtosis, and skewness by just using dot, and it will return these. Now, once we are
Sir, could you
done with
just
this,
explain the 44th row? Just lost it.
yeah,
44th
can you please
second row. Creating
this
an
one?
array. Yes, yes.
Yeah, so you just create a NumPy array. To create a NumPy array, you supply a list and it turns it into an array. That's it.
What's the value -1? It refers to last row.
No, these are basically just values. It's not -1 that it's the last row or something like that. For example, I have a list, let's say 1, 1, 1, something like that. Rather than keeping it as a list, I want to turn it into an array. So I just pass it to np.array. So this here is a list. So let's say I do type on this. It's a list. If I do a type and I supply the same thing to a NumPy array, it says np.n-dimensional array, but both print out the same thing. So let's say if I do print this, I say, do we have any addition of this? Yeah. So both generate the same thing. The only thing is you can do mathematics on this, you can't do math on this.
Thank you.
Okay. Yeah, so we have, let's say, DESC and so on. Now in stats or in any library in general, in Python, you will have several functions. So let's say I say stats.norm, and you don't know what this does basically. So a good thing to do is just write question mark, and it will generate a help basically of that class or that function. So is that visible? So let's say I do the same thing for describe. So it says compute several descriptive statistics of the passed array. Your parameter is a, which is an array-like object, and you can pass several other things, and it returns these things. Okay, so it's quite helpful when you're working with any library and you don't know how something works, what are the inputs, what are the outputs. Another way to do it is you pass it to a function called help. It's a basically function that Python provides. It prints out the same thing that you got on the side. It will print it down here. Okay. Now, how does this help or this question mark work behind the scene? Let's say we create a function func. It takes in x, and let's say it returns x. It does nothing basically, or maybe just x plus 10. So if you write production code, for example, or create any library, it is a good practice to have a description of basically your function here between these three codes. So let's say this is a dummy function that adds 10 to the input. If I run this and I call help on my function func, it prints the same thing. This is a dummy function that adds this, and I can also do the same thing with this. If I say question mark, it will return the same thing. So this is a dummy function that adds like this is this. So whenever people create any library, they always write this thing so that you can use this question mark or help to gain access to the docstring. This is called a docstring. So we did describe, we saw how to use a docstring. So moving on. So distributions. So in class you studied, let's say, a binomial distribution or maybe a Poisson distribution in your lectures. So in SciPy, what you can do is say stats dot binom, a binomial distribution, and it says a binomial discrete random variable, and you just have to supply how many. Just as basically a reminder, a binomial distribution is a repeated Bernoulli. That is, let's say in a binomial distribution with n times, it's the same as n coin tosses. Every coin toss has the same probability of having a success. So we'll say that I want a binomial distribution where I will conduct my experiment 10 times, and the probability is, let's say, 0.25 of success every time. Yeah, so it creates a distribution. I can save that distribution in a variable. So let's say dist or this. Okay, so we can check its mean and so on. So the mean is 0.25, and we can also have the variance. Yeah, so let's say you have a binomial distribution and you want to draw points out of this distribution. For as you normally do, that is, I give you a distribution and you say, okay, I want many points out of this. I want random variables out of this. So the way you do it is you say dis.rvs, random variables, and you say, let's say I want 5 variables. So it will draw them one at a time. So the first time it got 4 success, then second time 3 successes.
Then what is RVS? What function?
Random
Function is it?
variables.
Okay. Between
Yeah.
5. That's
Okay. So
Sir,
you
can you
created.
please explain the binom function?
Yeah, please repeat.
So can you please explain the binom function from stats?
This function.
Yes,
Yeah,
sir.
so let's say a binomial function. You know what's a binomial function, right?
Yes, sir.
Yeah, so it's just basically emulating that into code so that now you can access its density function, the cumulative function, and things like that. It creates an object out of your distribution so that you can quickly access things. You can create random variables out of that. You can sample things out of that. That's it. Here you are basically
Sir,
telling it,
how to set seed in Python, sir?
I
We set seeds in our programming language so that every time it will have the same list of random variables.
yeah,
Can we do that in Python?
yes, yes, yeah, we'll come to that. Yeah, we'll come to that. So in this distribution, I told it that I want to repeat basically my experiment 10 times. Every time I'll have a 0.25% chance of a success. So what he was saying was, let's say we do it here. I run it once. If I run it again, I may get something different. So the concept of randomness in computer science is not the same as in real life. So in computers, they use something known as pseudo randomness. Okay, so pseudo randomness, they have a generator, a random number generator, but it takes a seed. Okay, a seed is basically a starting point. It says, okay, I'll set my initial state based on this seed. Everything after this, I will create based on this. So let's say I say np dot random dot seed. I set it to, let's say, 7. My seed is 7, and I create these 1 4 2 3 5. The next time it again said 1 1 4 2 3 5. Could you repeat your question?
Hello?
Yeah,
So I'm not able to hear you.
you just heard me. Okay, so moving on.
The seed function actually it is used to apply some randomness into the distribution data.
No, it does not apply any randomness. What we said was, I mean, for example, in probability, you always have, you expect some randomness to be there, but you cannot emulate real life randomness in computers. So what they do is something known as pseudo randomness. That is, let's say in at random, if I generate numbers, let's say 1, 2, 7, 6, and 4. If I,
Yes, yes.
yeah, so I was saying if I repeat this task, I may get a different set of random numbers. Okay, but let's say for some reason I want to replicate, let's say on my side I created some random numbers. I send my code over to you, but I want the same random numbers to be generated on your side. Okay, they are still random, the sequence is random, but I want them to replicate every time a person runs the code. So to do that, you set a seed. Okay,
Okay, sir.
what this
Thank
does
you.
is it fixes the sequence of random numbers that will be generated.
And it is the
So
same
then,
throughout the iteration.
so then every time the same numbers will be there.
Yeah, yeah, yeah. So by the way, there's another
Okay.
thing that should be noted. Let's see if I do this twice here. Hmm. And if I do this here, 3 4 2 1 2 2, yeah. Hmm. Maybe in Colab it works fine. So just a heads up. Normally, when you write Python code, you would probably write in a script. A script is basically a single file where you run all of your code. Right now, we are working with notebooks. So in notebooks, you work with cells. So sometimes, for example, in VS Code, every cell needs its own seed. So it can't be that you will basically define this seed in the topmost cell and it will apply for all of the cells. In some cases, it happens that every cell needs its own seed. So just be aware of that if in case you utilize seeds in your code. It is safer to basically use, if you're using seeds, use them in every cell. because I've experienced it that some notebooks they don't propagate the seed to all of the cells. So as your question was, I mean, let's say if I run this again and again, I will every time generate the same sequence. The start will be the same. If I generate 100, the 100 random numbers will be the same every time I repeat the experiment. If I change the seed, the sequence will change. Let's say from 7, I change it to 70. Now we have 5, 4, 3, 4, 2. If I run it again, I have this. Earlier we had the seed set to 7. If I restore it to 7, I again get 1, 4, 2, 3, 5. So it is used to replicate sort of randomness. That is same randomness on every system. Sounds weird, but that's it. Okay, so returning to our point, so we were working with, let's say, distributions. So let's say this time we'll create a normal distribution. So we'll have stats.norm. A normal distribution takes two things. It requires a mean and it requires a standard deviation, right? So you supply mean as LOC, that is the location. Let's say it's 0, and the standard deviation as scale. Let's say we'll set it to 2, for example, and this is our distribution. By the way, it's okay if you forget these. That is what is LOC, what is scale, and what is basically RVS, random variables. It's a tip in general for programming. The goal is to know that something can be done. It's not important how you do it, what is the text that you write it. You should have a faint idea, okay, you can do this in Python. You can create a distribution in Python. You can extract random variables in Python. How do you do it? Which library can you use? You can anytime Google it out. There is no restriction on that. Okay, so rather than cramming the syntax, keep a mental note that you can do this. When it's time to do it, you can just do a Google search.
Sir, RVS stands for
Random variables.
random variable. Okay.
Sir, I have a doubt.
Mm-hmm.
So above, for binomial distribution, you had given the value of n and p. What do they stand for?
Yeah, so in a binomial distribution, you have to specify how many. N basically says how many experiments. If you remember what a binomial distribution is, it's essentially a repeated Bernoulli, right? Repeated coin toss or repeated anything that has two outcomes, and you repeat it many times. Every time you assign something as a success. In case of, let's say, a coin toss, you say a head is a success. So you say I have a 50% chance of a success. But let's say you had a loaded let's say coin and you had a 75% chance of a head. You will say this time my P is 0.75, and then you basically toss your coin 10 times. That's what this means. N is 10 and P is 0.75.
Okay, thank you.
Yeah. And these values basically RVS, this returns how many successes did I get. So last time I had set it to 25. It said I asked it for 5 random variables. That is the first time it ran the experiment. It did it 10 times and it succeeded only once. The second time it ran 10 experiments, it succeeded 4 times. So it is basically repeating the entire experiment as many times as I ask it to. Clear? Make sense?
Yes, sir.
Yes,
Okay.
sir.
Yes, sir.
Yeah. Yeah, so let's move to, let's say, for example, a normal distribution. In a normal distribution, you supply the mean and you supply the standard deviation. Okay, so we get a distribution here like this. Again, we can do the same thing. That is, from this distribution, give me random variables. Let's say give me 10 random variables. And it will generate random variables from this distribution. Okay, same as the previous case. So we've covered these two things. Binomial, and we have random variables and so on. Yeah. So in any distribution, there are three things that you care about: the density function, the mass function, and the cumulative this. If we see, Yeah. So let's say you are working with a continuous distribution, you will be interested in the density function and the cumulative density function. If you're working with a discrete function, let's say a Bernoulli, you'll be interested in the mass function and the cumulative mass function. Okay. So rather than writing the entire formula or coding it up, that is, for example, let's say in case of a Bernoulli, or basically a binomial, you will say n choose s successes p to s and so on. Rather than doing that, you can simply say, for example, I have a distribution same as above, stats binomial distribution, 10 coin tosses, and every coin toss has, let's say, a 20% chance of success. I can use distribution dot pmf, and I can pass, let's say I ask it, okay, I made 10 coin tosses. What are the odds that 5 of them were heads? So this is the chance. Okay, exactly 5 of them are heads. Let's say I ask it, what are the odds that all 10 of them are heads? This is the chance. Okay, so let's say what are the chances that 100 heads are there? Zero chance, because I only tossed the coin 10 times. Okay, make sense?
So how is that value 0.0? How do we actually? What is that 0.0 from probability mass function?
Yeah, so in a discrete, when you're working with discrete probabilities, a PMF of x, let's say at x, returns the probability that I have x basically values. In this case, in a binomial, when I say what is the probability mass function at 100, I'm asking it what is the probability of getting 100 heads when I toss the coin 10 times. So there is no chance I will get 100 heads. That's why the probability is 0. If I ask it, let's say 5 heads, there will be some probability. So we have 0.02. Make sense?
Sir, I think if we plot the histogram, it is very clear, sir. If we plot the histogram chart of the binomial distribution, it will be very clear, sir.
Yeah, we'll get to that. Actually, we're going step by step. I want to cover PMF, CMF, and then we'll get to plots rather than jumping to plots directly. Okay, so
when are we actually using all this PDF, CDF, and PMF in what kind of applications of real life?
So in real life, I mean, you may not use these directly. It will probably come up in a bigger function. So let's say at some point in time, let's say create a machine learning model, and your weights, basically you may want to draw them out of a Bernoulli distribution or a binomial. There you may use that. And in this case, for example, again the same thing. Let's say someone asks you to compute this very thing. Let's say on the fly they say, okay, toss the coin this many times, give me the odds that you get 5 heads. So these are toy examples, but basically you can employ them whenever you basically see such a situation that, okay, this resembles a binomial distribution. So let me basically use the mass function or maybe the cumulative distribution.
Yes.
Yeah. So let's say you have a normal distribution where your mean is, let's say, 1, and your standard deviation is, let's say, 2, and you want to find out what are the chances that let's say a value x is, let's say, between, or maybe let's say it is less than, let's say 2, for example. So for that we will basically use this dot CDF. A CDF basically says, if I ask it to, let's say, to do for x, a CDF says what are the odds that you are less or equal to x. So that is exactly what we are looking for. That is, what are the odds that I am below 2. So if I pass in, my mean is 1 basically. So let's say if I do this, I have a 0.5 chance basically. Our normal distribution is centered at 1. So half of this is on the right side, half of it is on the left side. So I'm asking it, what are the odds that basically I belong to the distribution if my value is 1? So there's a 50% chance because I'm right in the middle. Does anyone have any confusion with using these probability mass function, cumulative distribution function?
So actually difference between all these three, if it could be explained.
Yeah, these were actually covered in your lectures. So every time, every week when you attend the live session, it is better that you go over your lectures, because the idea is whatever you cover in your lectures, we will try to put that into basically Python. So it will be difficult.
Okay, so I'll look into it.
Yeah, because then it would become a repetition.
So we can't use.
Can you please take your answer, sir?
Yeah, please speak one at a time.
I could not understand anything from the lecture. First, I can go on.
Or you could not understand it from the lecture.
Yes, sir.
Or my lecture or the
video,
professor?
all the videos. Professional, sir. Professional. All
Okay,
right.
so
little bit.
I mean, I would.
Or later you can share it.
That's.
Yeah, I can
maybe. Second.
Yeah, so for probability, I can share a resource. I mean, I can't cover it right now because I mean, it's almost 8. And these sessions are geared towards basically programming. That is, whatever you do on the theoretical part, how can you do it in code? So I can recommend, for example, this book for probability. It's a very renowned book. So its name is A First Course in Probability by Sheldon Ross. So you can use this for probability. I don't know if it has a free version available online, but it's a very good book. So if you want to cover probability, you can do these.
Yes,
and in general, if you're facing, I mean, if the professor's lectures are maybe not, I mean, not conducive for you, you can opt out anytime. I mean, you can spend the same time on a different course, right?
Could you explain the lock equal to 1 and scale equal to 2 once again? What's the use of that actually?
This part.
Yeah, that's it.
Yeah, so it would be actually okay. Let me maybe show you the plots, right? By the way, did you note this down? If anyone needs this, I mean, read this book. This way. Yeah. So I was saying, yeah. So let's say you want to visualize these distributions. So let's say, let me show you what a normal distribution looks like. So a normal distribution looks something like this, where the peak of the normal distribution is the mean, and the standard deviation tells you about the spread. Okay, so let's say I create a distribution stats dot norm, and LOC is 0 and scale is equal to 1. If I want to basically plot this, I need 2 libraries.
Matplotlib.
Yeah, Matplotlib and SciPy. So let's say what I do is SNS dot displot, and I say give me a lot of random variables, and let me plot this.
Hello.
So what does Seaborn do here?
Hello.
Yeah.
Oh, बघितलं.
Yeah, can you repeat?
So what does Seaborn do here?
Yeah, Seaborn is basically a plotting library. Matplotlib and Seaborn, they are used to visualize your distributions or anything, basically a plot or a line, something. I will go over it maybe in a minute. Yeah, Matplotlib and Seaborn.
Yes,
you
but
can.
you're using both here, so I want to know the difference.
Yeah, so basically, Matplotlib was an earlier version. Seaborn is a relatively new library, and it looks basically more aesthetic compared to Matplotlib. For example, if this sns.set basically says set the visualizations to conform with Seaborn standards. So Matplotlib, this would be relatively ugly.
Okay.
Seaborn has some functions. For example, this displot. Displot says plot the distribution. This function is not available in Python. So for example, if we look at this is the distribution that we have generated here. That is dist stats.norm, and we are plotting the distribution. Notice that the peak is under 0, and as we move away, it drastically drops down. So a better way maybe to do it would be, let's say you say yeah, something like this. Okay, so it's not as smooth as we saw in the figure here, because we are essentially generating lots of random numbers, and it may happen that it did not generate enough random numbers here in this space. So to get an idea, a better way to do it is you supply the values itself and ask it to compute the basically probability. So generate a sequence of x values, compute the proba of each x value, and then plot x and y. Okay, so the way you generate a lot of x values equally spaced is np dot linear space. Basically you tell it, okay, give me numbers. Let's say in our case I'll ask it for -5 to 5, and I'll say give me 100 points between -5 and 5. Okay, let's say np.lin space, I ask it from -1 to 1, I ask it for 10 numbers. It will generate it like this, equally spaced 10 numbers. So right now I'm asking it, okay, give me from -5 to 5 100 numbers. So let's store it in x. If we want the probabilities of each of these numbers, what we do is we had this distribution. Let's take it out. We had this distribution. So what we want is, this is a, oops, we want the PDF of x, and we will save it in y, and then we just say plt.plot x and y. Yeah, so you see we have a smooth curve this time because we ourselves supplied all the values.
PLT refers to matplot, is it? Matplotlib library, PLT.
Yeah, PLT refers to matplotlib. We imported it as PLT.
Okay.
Yeah, so maybe you'll need a primer on these two, basically SNS and PLT. Yeah, let me show you just a bit.
Sir, could you just focus on that location? If you change that location equal to 1 or 2 and scale equal to, if you change. Yeah.
So let's say
how it will change the plot.
Yeah, let me show you. Let's say we directly supply it here. We had linspace, and we'll say y is stats dot norm distribution, supplied x. Initially the location is 0, and let's say the scale is equal to 1. Let's create another one where the scale is 2. Let's create another one where the scale is 3. This is y2, this is y1, this is y3, and let's plot all of them one by one. So we have y1, y2, y3, and we do this. LOC. Oh. Yeah, so can you see this? Yeah, let me show you something here. For example, label is equal to scale equals 1, scale is 2, scale is 3, and when I plot it, I plot the legend as well. Yeah, so we see that when the scale is 1, we get the blue distribution. When we increase the scale is essentially the standard deviation, so we get a spread out graph. When we increase it further, the spread increases even more. Every time the mean remains the same because we haven't changed that. LOC is 0 for every one of them. The standard deviation changes. If I change LOC for, let's say, 1, we'll see that the orange graph has shifted to 1. Does that clear the confusion?
Okay, so basically we are assigning it a mean value that it is like a standard normal distribution, it is 0, and in other normal distribution, the location will decide the mean, right? And the scale is somehow, if we are keeping the same mean, but we are changing the kind of it is change. We are changing scale is the standard deviation, right? Can we say that?
They are just aliases. Yeah, basically they are just aliases. LOC is same as mean. No. Scale is same as standard deviation.
Yeah, standard deviation. Yeah, that would okay. Okay, thank you.
Yeah. But I have a question. Like, why did we, change the scale? And is it dependent on the standard deviation, or in this case, we just try to see if
the scale is the same as scale and standard deviation are the same thing. They have just named it different. It's not dependent on STD. Okay. It is STD.
Okay. Suppose in production, like if I wanted to assign the standard deviation as a scale, in place of 1, 2, 3, I should substitute the standard deviation, right?
Yeah, exactly.
Okay.
Yeah. You can also write it like this. For example, mean is 0, STD is 1, and you say this is STD and this is mean, and it works. Okay. Yeah, so just in case, I mean, in this case, I did not store the distribution in a separate variable because I just wanted the PDFs. So ideally what I mean, if we did it the way we did it before, that is save the distribution and then create the PDF, we would need 3 more variables, dist1, dist2, dist3. So rather than doing that, I just access the PDFs. Okay, so maybe some of you may be thinking, where did we store the distributions? So does this make sense? Does anyone have any confusion with all of this? I mean, if you're not familiar with maybe Matplotlib and Seaborn, this may be confusing, but those who are familiar, is it okay for you? Can I have a raise of hand maybe? Yeah, okay, thank you. So we have covered plotting the distributions. We have this. Yeah, so another thing which I'd like to show is the difference between these plots and this plot. So in this case, what we did was we generated a lot of random variables and we hoped that it will cover the entire range. The only problem is it may miss out on certain values in certain intervals, creating a function that may not be perfect. In this case, that did not happen because we ourselves supplied the intervals, every value in every interval, there are exactly the same number of points. So you get a smooth function. Okay. So let's say, so this is useful basically when you have a lot of numbers, but you don't know their distribution. Okay. So for example, if I create a NumPy array, np dot random dot normal, or maybe let's use SciPy. So we have stats dot normal distribution, and I want a lot of random variables. LOC, let's set it to, let's say 1, and scale. Yeah. Please repeat. Okay, so let's say we have a lot of random variables and we have stored them in, let's say, this var. And if I, let's say, store them in a file and send them over to you, and I don't tell you that I have used a normal distribution and I have used this mean and this thing. So there, a quick way to do it may be this, that is, you just pass them to displot. That is, okay, just plot these and I'll guess the distribution myself. So when I look at this graph, I see exactly how many variables are in which bin, and I can guess, okay, this looks like a bell curve, so it is probably a binomial distribution. Notice that in this case, we cannot supply our own variables. These are constants, okay, from -5 to 5, give me 100 values. But let's say someone sent you a bunch of numbers and asked you, okay, tell me which distribution do they belong to. You cannot use this, okay. So in that case, using a displot is very important, becomes very handy. You can just pass them over. It will basically assess the bins itself, and you can guess, okay, this looks like a binomial distribution. You can play around with the number of bins. Let's say you say, okay, give me only 10 bins. It will generate the plot with only 10 bins. And you can also tell it to do that I don't want these histogram bars, give me a smooth function. That is, just connect these points. So what you can do is kind is equal to KDE. Yeah, you don't need bins in this case. And then it will give you a function like this, as we did it before, okay? Now, this you can also supply.
Sir, what key means? What is the full form of KDE?
KD is basically for a density plot. It converts, I mean, normally when we do this, it calculates the frequency of every bin and then plots them. When we supply KDE, basically kernel density, it turns it into a PDF. It applies those restrictions, that is, the area under the curve should be 1, and basically it turns them from this space to the probability space. It is a short form for kernel, I believe, KDE plot, kernel density estimate.
And what about SNS?
SNS is just CBORD.
It's
SNS is the library.
It's a library. Okay.
So maybe after lecture, you people should go over these.
There was some concept of bins. I didn't understand.
There was some.
There was some concept of bins. BINS.
Yeah, bins.
What is it actually related to? What does it say regarding distribution?
Yeah, so whenever you create a histogram, you have to assign bins basically. So what bins are, for example, I ask it, okay, the first bin is 0 to 10. The next bin is 11 to 20. So these are bins. A value that falls between 0 to 10 will add one number to that bin. So for example, in this case, let's say this bar goes up to, for example, 110. So this bin contains 110 elements from our case. So I can, so by default, Seaborn itself calculates the best number of bins, but I can hard code that. So I can say, okay,
20, 40, 60 are bins. 80, 100, these are bins.
Yeah, for example, in this case, our bins, they look like, for example, going from, let's say, 0. Maybe, for example, from 1 to 2, and this is from this to this. So these are bins basically.
The ranges.
Yeah, the total number of buckets, you can think of them as buckets. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here we have 10 bins. We supply 10 bins.
Oh, okay.
Yeah. So I was saying, so for example, in this case, it has created, if we supply kind is equal to KDE, it basically converts it into a PDF. But let's say I want a cumulative function, that is a CDF. All you have to do is say cumulative is equal to true. And it turns it into a cumulative function. A cumulative function basically sums up everything up to that point in the previous graph. So cumulative equal to false gives you a density function. Cumulative equal to true gives you a cumulative mass function, a cumulative density function basically. Any questions?
Cumulative refers to the average plot of the function.
For cumulative?
That graph was a linear graph in the sense it was sigmoid graph.
For example, yeah. So let me show you. Yeah, for example, wait a second. Maybe. So ignore this part. I mean, it may not make sense to you. Same thing as over. Still under. Yeah, so the way you generate this plot, basically what you do is, for example, at -5, you sum up the values. This is the area under -15 to -5. That is the value of this graph here. Okay. The same thing happens, that is when you reach 0, it has all the area up to this point. It represents it here. Okay. Similarly, after that, the values dip quite quickly. So you see a saturation when it reaches, for example, after 0 to 0.5, it reaches a saturated value. Makes sense?
It doesn't take the mean of the whole values which are there after 0 to the 1. That is what cumulative does.
No, a cumulative thing basically means sum up to this point. So a cumulative value up to 0 means from -infinity to 0, give me the area of that point, basically. So for example, if you work with continuous distributions, you will, for example, I ask you the probability of x is less or equal to 5. You will use the cumulative distribution and find this value. This will be a probability.
Okay, sir.
You were stating an application, actually I got disconnected for a while, that the using of weights in case of data, a huge amount of chunk of data in AI, if you're using this, you were saying something about that earlier.
Yeah, so I was saying, yeah, a use case.
As an application point of view.
So let's say there is a field known as, let's say, reinforcement learning. Reinforcement learning, what you do is, for example, you have games like chess, or for example, a car driving. You have an environment, and for example, this, and you have to decide on an action. So sometimes what it happens is, and you have several actions, that is A is an action, C is an action, B is an action, so on. And you want the model, basically your object, to decide an action using a probability distribution. So for example, if you ask it that, okay, draw an action based on a Bernoulli distribution, draw an action based on a multinolly, or a binomial, there you can use that. Does that make sense?
Somewhat. Okay.
Yeah, so basically I'm saying sometimes what happens is you have a large distribution and you have to pick objects. So rather than picking, so let's say for example you had let's say you have a robot and for example let's say you have a for example you have a graph. Do you know what a graph is in computer science? Just nodes connected by edges.
Yeah, fine.
Yeah.
Yes.
So let's say at any point you have only two options: delete the edge, add an edge. Okay.
Okay.
Right. So you can map this to basically a coin toss, right? A Bernoulli.
Fine.
And you can assign weights that, okay, I want addition to have more weight. I basically think of addition maybe as a success, and I assign it more weight. That is, there is a 75% chance that I will draw addition, but there is still a 25% chance of drawing a deletion of an edge. So there you can basically say, okay, take this space as a Bernoulli distribution and draw them basically like this, random variables, and draw them out of this. And then you have basically a chance of getting both. If you did not have these distributions, you would have to hard code it. That is, either give me addition every time, give me deletion every time. I mean, think about it. How will you tell it that 75% of the time give me this, 25% of the time give me this? How will you induce this randomness into your robot? So there you can utilize these distributions.
Okay.
Makes sense? Okay.
So just trying to understand here. Let's say I have n number of customers using these series like Bernoulli's or binomial series. Can I categorize them that okay, today I need to, I mean the probability that today I may get 15 customers because of these events, or is it the application? Can I take an example?
Yeah, so I mean, it would be very simplistic to predict based on this, because I mean, you can do it, but it would be very simple. For example, let's assume a question. Let's say you are a salesman and you receive, for example, some machine. Let's say you receive machines M, okay, machines M, and historically you have noticed that your seller, let's say he sends you M machines, 5% of them are usually defective. And today you receive 10 machines. So how many of them would be defective? An estimate. You can create an estimate and then you can accordingly plan your budget that maybe I'll receive this much loss and so on. Make sense?
Yeah.
Yeah.
Right.
Okay, so
you were talking about the libraries that we need to watch out for the plots or the matplotlib and seaborn. Any other libraries that we need to be knowing
seaborn. That's it. These two.
Okay. Fine. Okay. Thank you.
I mean, I do not expect that you knew this in this session because you were not taught it in the course. That's why I stuck to only this part, that is displot, one line. Apart from that, it's a whole library that you can play around with, and it's easy to learn. There's not much to do in that. I mean, you get the hang of it over time. Maybe if we get time at the end of the session, maybe I'll give you a quick run over this.
Also, sorry to interrupt. You said the graphs, right? Adding an edge and deleting an edge depending on some rules. So which library is more apt for describing or depicting the graph in my data? Like I have some customer, let's say banking customers. You have account holders. I wanted to check between account holders only, like is there any transfers happening today? I have 15 customers and I feel that customer A or 15th customer is transferring to 8th customer today.
Normally you would have an entire class for such things. If you are aware of classes in Python, right?
Class in the sense hoops concept you're talking
about? Yeah, exactly. Yeah. So you will have something like this, a customer and so on, and then you can have interactions within that. Let's say for example you use something like a social network, okay, where people are connected to others. Normally what you would do is there is a library known as PyTorch geometric. Okay, so PyTorch geometric, it works with graph neural networks.
Okay.
So these are specialized neural networks to work on graphs. So they have been basically, they have already created these data structures for having a graph, having connections between graphs, every node having a feature, every edge having a feature. If you don't want to work with graph neural networks, but you only want to work with graphs, then there is a library known as NetworkX. This works with graphs, but I mean, they will be more, I mean, focused on graph theory rather than neural networks. So if it's, I mean, useful to you, you can look into these two.
Yeah, I'll check. Thank you.
Okay. So just a little bit of practice for you guys. I think we've covered a lot of things today. So for example, in this part, SciPy, we did describe initially. We saw what a docstring is. Then we saw how to create a distribution. Then we saw how do you sample variables, basically using RBS. Then you saw how to use, let's say, a PMF, a PDF, or a CDF. And then you saw how to plot a distribution using np.linspace and np.hist, plt.hist rather. And you saw how to plot variables, basically how to plot variables to guess a distribution using sns.dist. Okay, so these are the things you learned in this session. So maybe try a few things just for practice. Okay, so there is a claim in normal distributions, basically distributions like this. If you look at this, do you see this figure?
Yes, sir.
Yeah, so a normal distribution claims that within one standard deviation from the mean, 68% of the data is covered. Within two standard deviations from the mean, 95% of the data is covered. And within three distributions, 99.7% of the data is covered. So can you verify this using what we have learned today? Try it out. So let's say we have confirmed 68% lies within one STD. 95% lies within two STD, and 99.7 lies within 3 STD. Can you some way confirm this? Try it out. It's 8:24. Let's wait maybe till 10 minutes. If you're done, raise your hand.
Seems new to me, so maybe I will wait for your explanation.
Okay, no issues.
Sir, I have a doubt. So binomial distribution is a discrete distribution, right?
Yes, discrete.
So what will happen if we use probability density function like .pdf? Do we get an error?
No, wait. So let's say we have a PDF. I think it won't have that function. Let's say we have stats.binom, and let's say I do 10 experiments, and let's say the probability is 50%. And let's say I say this.pdf, right?
Yes, sir.
Yeah, just a minute, it's running.
that it is not perfectly coming to 68%, sir, but it is close to 68.
Approximately.
Okay. Done.
Yeah, it says it doesn't have an attribute PDF because it's a discrete distribution. So if I said, let's say PMF, it would run. Clear?
Yes, sir. Thank you, sir.
So let me repeat the question. So for people who are still trying, when you are given a Gaussian distribution, the assumption is that, I mean, your data set follows the Gaussian distribution. It means that the claim is that 68% of the data will lie within one standard deviation of your mean. Okay, so let's say I give you some number. So and I just randomly ask you what are the odds that what is the probability that it will be within one standard deviation, you will say there is 60%, 68% chance that it will lie between these two. Similarly, what is the chance that it will lie within 2 STD? 95%. Similarly, 3 STD, 97. Let's say I ask you what is the chance at 10 STD? It is essentially 1 because everything is covered. So you can even probably take a hint from this. What basically is required? You are required to compute this area, the dark green area.
Sir, done.
Yeah, so the people who are done, please raise your hand. Yeah.
Wow.
By the way, I wanted to know something. Do you people have access basically to all of these sessions? For example, I'm not the only one conducting these sessions. There will be multiple TAs. So are you aware that there are multiple sessions?
Yes, I think also.
Yeah, so basically every researcher, every research scholar has been assigned to a separate day, and everyone has their own meeting. So based on your preference, maybe your taste and maybe your availability, you can decide to go with any one of them, and everyone uploads the lectures on YouTube, and I'm not sure whether they share the code or not. So do you have access? Basically, do they send you the YouTube playlist or the channel? Is that accessible to you?
Yes. Like to access the YouTube videos, like on the every Friday there is a lecture from the session, so I'm also able to access. But I'm not able to access the lecture which is on the between the Monday to within the Monday to Friday due to the office work.
So I'm saying, I mean, does the faculty inform you? For example, do the support staff inform you of these lectures, or does the instructor, for example, like I am informing you of my videos, did you receive a mail from the faculty about them?
Yes, actually, I'm receiving the mail as well as I'm also receiving the notification on the what we call as spam portal.
Okay, so
Yes,
for example,
we saved all the YouTube channels.
so I mean, why do students then ask me that where will the lectures be uploaded if you have already received the emails for the basically the channels?
I think previously, like on the last week lecture, you have shared the playlist with us.
Yeah, I sent it, but the problem is, let's say some new person joins the session today. He is not aware of the playlist. Okay, so anyways, so what we are looking for here is basically the area up to this point, right? So I want the area, this dark green area. To compute this dark area, what I can do is I can compute the area from minus infinity up to this point, and I compute the area from minus infinity up to this point. Subtract the latter from the former, and I will get this area. Does that make sense?
Yeah, it made sense totally. While coding, that is, we are not actually not very familiar with the code, so coding.
Yeah, okay. I mean, just saying the concept is there, right? So how do I get the area from this point to this point, right? That is essentially the probability that I will lie less or equal to one standard deviation. So in this case, exactly, yeah, the CDF. So for example, I have a normal distribution and the location is, for example, 0, and the scale will set it to STD is, for example, 2, let's say 1. So the STD is this, and I say give me the CDF at STD into 1, that is 1 STD. Okay, so this is the value here. I can also say give me the area from this to this point. This point is essentially minus STD, right? From mean go to the left 1 STD, so that is minus STD. So I can say this into -1, or essentially cited like this. And now I just subtract the two. So we do this minus this, and we see 68%, right? Similarly, instead of 1 STD, if I supply 2 STD, 2 on the right side, 2 on the left side, I get 95%, and 3 STD, I get 99.7%. Okay.
Could you try 10?
10 STD.
Yeah.
1.
Okay, thank you.
Yeah. So this was, let's say, confirm
just a bit conceptual question, right? When we are stating that STD is equal to 1, right? We are putting the value. Is it actually the standard deviation? I'm not exactly able to get that. It is kind of a x-axis scale where the mean is there, and the standard deviation is the division of the whole graph, that the y part or the bell part, right? So when we are putting here 1, I was actually, while solving it, actually I had a doubt that what standard deviation value I will put there, right? So that is why I could not. CDF was fine, but so I'm not exactly, when we are putting here STD is equal to 1, how is it assigning it as a standard deviation? That I not.
Yeah, so the thing is, actually we use the same STD here and here. So for example, if this STD was set to, let's say 2, and then I used 1 STD, 2 STD, the thing is I'm taking multiples of the STD I used earlier, right? So that is why it was working. So for example, if I did not set this variable and I manually set it to 2, if I wanted to check within 2 STD, I would do 2 into 2. So that is would be 4, and the other way would be -4. If I had, let's say, for example, 1.5, within 1 STD would be 1 times 1.5. So basically I'm setting 1.5 from the mean. Okay. That is also the case because the location is 0. In case the location was, let's say 3, I would have to supply maybe 3 plus 1 standard deviation. Does that make sense?
Could you just elaborate a bit further? This why the double 2 into 2 4 why it was done exactly? Not sure. When it is scale is equal to 2. So how does it? Could you just do once more? It was just too fast.
Okay. So basically, we're setting. Let's say we have our mean is equal to 3, and the standard deviation is 2. For example, yeah, we create a distribution.
We could go with mean equal to 0. That is, 0 is fine. Mean is equal to 0 is simpler to understand.
Yeah, so that would be simpler because you won't have to add anything at that point.
Okay, no problem. No, yeah.
Yeah, so the mean is 0 and the standard deviation is 2. And
yeah,
what we want is, so let's say if we plot it, SNS dot dis plot, we say dis dot res, give me a bunch of random variables, and kind is KDE. Yeah, so what we want is, in this case, where did we create the distribution? Yeah, so the STD is 2 and the mean is, so I am essentially looking for my area up to this point here.
Yes.
Okay, so this point I basically have to supply x, this x value, and it will compute area up to x equal to this point. So x is equal to 1 STD, right? I want to compute my area where x is equal to 1 times whatever STD I set, right?
Yes.
Yeah, and then I want to do the same on the left hand side, that is area from minus infinity up to STD left of the mean. Okay, so for example, in this graph, the first case, 1 STD is this dotted line. So area from this to this is STD on the right side. Then we have 1 STD on the left side. So area from minus infinity up to this point. Okay, so when we subtract the two, we get the area in between.
Yeah, the area is part is clear. I'm just trying to understand. Even the code part is fine. I'm agreeing with the code. I'm just saying the x-axis value. Supposedly this is 0. This is 2.5. Are they actually? Can we call 2.5 as a standard deviation?
No, this is not standard deviation. Yeah, these are just labels. These are just for reference. The numbers that are on the plot, they are just for reference. I can even pass them myself, I believe. So for example, if I say plt.xticks, I'll say give me values from, let's say, -4, -3, -2, -1, 0, 1, 2, 3, 4. And then I do plt.show. So you see the ticks have changed.
Yeah.
Yeah, so you can set them yourself. For example, in this case, because our standard deviation was 2, this is one standard deviation from 0 up to 2. Is it clear now?
Yes.
Okay. So for example, let's try another problem. So let us try the problem that we just discussed a moment ago. Okay, defective items. Let's say you are a seller, okay, and you receive items. 5% of those items are always defective. Every machine, every item is the same. It's just that whenever you receive something, 5% of them are defective. Okay, so what happens this time is you receive 10 items, okay, 10 machines. So what is the probability that 2 items are defective? So can you use SciPy to find this value? Try to fit this scenario in one of the distributions that you know of, and then you can use the distribution, the PDF, CDF, and so on. Think about it.
Sir, approximately 7.5%, sir.
So did you do it by hand or did you do it through this?
I use PMF function, sir.
Okay, so
Probably
let's wait. Maybe let's wait for 5 minutes. I mean, let others try.
Okay.
Yeah, it's good that you did it. Yeah. Yes, Rohit, you have a question?
Point 0.0746. Yeah.
Oh. By the way, one more thing, there are multiple live sessions for this course, but you're not obliged to see all of them. You can stick to any one of the researchers and then continue with them. It's not obligatory that you cover all of them because it would become quite hectic for you. Okay, so it's 8:45, so let's get started. The idea is you receive an item and every item is the same. Every item has a 5% chance of being defective. So think of it like this. You have a lot of coins. Every coin is identical and every coin has a 5% chance of getting ahead. Okay, so it is clearly a binomial. It fits the binomial distribution. So if we create our distribution, let's say stats dot binomial, and we'll repeat our experiment 10 times, and the probability of hitting a head, or in this case being defective, is 5%. Okay, so if we write it like this, then what we have to do is from this distribution use its PMF and supply 2. That is, what are the odds that 2 items are incorrect, are basically defective. So we get 0.0746, which is essentially 7. Yeah, that's the same. Yeah. So did everyone get this? Any confusion?
Yeah, if it would have said that less than 5, then we would have used the CDF for that purpose. Less than
Yes,
5
yes.
items are defective.
Yes, less or equal to 5.
Thank you.
Yeah. So
Yeah.
let's try the last question for today. So let's say MCQ. So a person is attempting a test that has 90 questions. Okay. Every question has 4 options. One of them are correct. One is correct. Okay. And there is obviously a 0.25% chance that he will give the correct answer. So he's answering randomly. What is the probability that student X scores gets at least 10 questions correct? Is the question clear? There is a student named X. He is attempting a test. The test has 90 questions. He will attempt every one of them and he will answer at random. Okay. What are the odds that, what is the probability that he gets at least 10 of them correct?
Sir, I have a question with regards to the previous question. Sir, I have a doubt. So we said that since the number of items are 5, in this case, we are going with the probability mass function.
So we have 10 items.
Okay. So if it was 5, then we would have used CDF.
No. So the question was, for example, in case of discrete probability distributions, PDs, for example, for short, the PMF gives you the probability of an exact number. So let's say I ask you what is the probability that 2 items are defective, you will use the probability mass function. If I asked you what is the probability that at most 2 items will be defective, that is either 0, 1 or 2, then you would use the CDF, cumulative density function. Okay. A PMF gives you the value at the exact point that you're asking it. CMF says this value or anything less than that.
All right.
What about PDF, sir? PDF.
Yeah, so PDF is used for continuous distribution, not for discrete distribution.
So I have a doubt. If we specify the probability of success as 95% and supply 8 into the PMF function, what will get?
So just replace probability as 95. That is, every item there is a 95% chance that it is defective. And then you're asking it, what are the odds that out of 10, how many should be defective?
8, sir.
Yeah, so it says there is the chance of 0.7 basically. So that is 7.4% chance.
The same chance, sir, for previous one.
This is the same chance. ये कैसे है?
Sir, it was nearly 99.9%, sir.
Yeah, it should be. Just a second.
But I have a doubt, sir. From what we should, did we include the CDF of 10 or not, sir?
Oh, so I think there's the mistake. So let's say if I do this, still the same. So let's say I have this and then I have PDF and then I say K is 8 and I print this. second. There is 0.95% chance. So if I supply, does it give the same answer? So it does not give the same answer.
There is a 5% chance for the item to be defective. Then there is a 95% chance for each item to not to be defective, right, sir?
Mm-hmm. Yeah.
And
okay, yeah.
We are checking for 2 items are defective. Then 8 items will not be defective, right?
So let's say I supply 2. For example, if we repeat the above question, that is 5 items are defective. And in our case, we say that being defective is good, that it is a success. We repeat it 10 times and we want 2 of them to be defective. So what do we expect?
So just the opposite of this, sir.
Mm-hmm. So is this incorrect? So is that what you're saying?
No, it's not incorrect. So it's perfect.
No, sir, it's correct.
Okay, so is there any basically confusion?
No, sir, here we have taken the probability of success as being defective.
Yes.
So in case if we take the probability of success as not being defective, we get the same answer.
Yeah. So then you can just do 1 minus that.
Yes, sir. Okay, sir.
Hi, yeah, if we change the number of items in the last question, like n was equal to 10, if we make it 5, then I think that will change now the probability.
Yeah. Yes.
Right. Okay.
Whenever you see binomial, just think of coin tosses. It's the easiest way to visualize it. Do 10 coin tosses. What are the odds that 2 of them will be heads? Exactly 2 of them. Note that it doesn't say at least 2 of them. It says exactly 2 of them. That is why the probability dips. If I said at least 2, then it may be higher. Exactly 2. It's actually important here. What is the probability? Exactly 2 items are defective. So was anyone able to do this one, the MCQ question?
Yeah, sir.
So can you share with the class how you did it?
Yes, sir. It was approximately 99.97%, sir.
And what was the logic behind it?
I create a distribution with binomial n is equal to 90, p is equal to 0.25, and like 1 minus the CDF of the distribution at 9.
Why at 9 and not 10?
Because in the question it is at least 10. So
yes.
The 10
yeah, excellent, correct. So the first thing to notice is that every question has a 0.25% chance. So every question is independent of the other. So we can assume a binomial distribution where, so we say, let's say stats dot a normal distribution. And in this case, we'll have 90 questions. And every question has a 0.25% chance of being correct, right? So in this distribution, what we want is at least 10 should be correct. So how do we do that? So for example, let's say we
it should be binom.
Yeah.
It should be binom or norm.
Sorry, binomial. Wrote it wrong. Yeah, so we have a binomial distribution. So what are the, if I want to check that is at least 10 means, for example, if I use the CDF at 10, what does that give me? That says what are the chances that I will score 10 correct or less, right? So what is the opposite of at least 10?
At most 9.
Yes. So we have at most 9 should be incorrect, right? So what we do here is we apply the CDF and we say k is equal to 9. It is important to use 9 rather than 10. Okay. So what is this telling us? this says that you have this much chance so that you will have exactly 9 questions correct. Right? And 1 minus this basically says if we, yeah, if we think of a graph, basically it says beyond this. I mean, does this make sense? What we're doing here?
Yes.
Yeah, can we have a raise of hand for this?
Sir, if you could
Okay.
explain why A is 9 there, that would be helpful. Just once.
Yeah, why is 9 there? Yeah. So the thing is, if I said, what is the probability that X gets more than 10? Okay. If I said more than 10, then we would have supplied 10 basically. So the thing is, the CDF says probability that X is less or, let's write like that, X is less or equal to this, for example. This is what my CDF tells me. So if I supply 10 here and then I do 1 minus this, I take away 10 from my answer. I want 10 in there because it says at least. So I cut the graph up to 9 and I take the rest. Does that make sense?
Yes, yes. Thank you.
Yeah. So that was the last question for today. So let me share the playlist and the repository for people who are new here. So every live session, you will find the code. Where is it? Yeah, so for every live session, you will find the code here. For example, the week 1 notebook is here. Similarly, this notebook, I will post it after a while. So let me share the link with you. And as far as the lectures are concerned, you will find the lectures at this playlist. It is also available on the GitHub repo, the link for that. So YouTube is this. So can you confirm if you can access both of them? Okay, so we'll end the session here. I hope it was helpful for you.